Tea time. Today's topic is linear modeling. So first and we'll go over the theory behind linear modeling, just a basic introduction to the concepts, and then we'll practically step through some code and see how to implement simple linear regression models in R. So to start, we start with simple linear regression. So you have the form of the equation is y equals beta naught plus beta 1 x plus epsilon, where here y is your response. That is your dependent variable. That's what you're trying to predict. X is your predictor, and that is the independent variable. Beta naught represents your intercept. So it's basically the value y takes when x is 0. And then beta 1 represents the slope. So the way we think about the slope is it is the expected change in our response y per unit change in x. And lastly, we like to add the term epsilon. That is our random error with a mean of 0 and unknown variance sigma squared. Okay, so in order to perform simple linear regression, we use one method is the method of least squares. And so say you have a pair of n observations where each observation fulfills the equation yi equals beta naught plus beta 1 xi plus epsilon I. Um, So the residual sum of squares is just the sum of the errors squared, and given by that equation right here. And the method of least square, the goal is to basically minimize this RSS. That's the goal. And so the way you go in minimizing that is you just take the derivative and set it to 0, and you get these two equations. And then if you simplify them, you get the least square normal equations. And once we've reached here, we can solve for beta naught and beta 1. Notice that we have uh, a hat on top of beta naught and beta 1 because they are estimated parameters. It's impossible to know the true values. Um, and so we come up with least square estimates for the intercept and slope. That is your beta naught and beta 1 hat. And these are the equations. And here x bar and y naught simply denote y bar denote the mean of y and x. That is, you sum over all the terms and divided by the number of terms. Um, then let's talk about a few more terms like residuals. So we have the equation y hat equals beta hat naught plus beta 1 hat x. And if you notice the difference between this equation here and this one here, you see there is no error term. That is because y hat represents the value, represents the estimated value. But just yi, that represents your true value. And so it's almost impossible to get a perfect model. And so we have to have an error term that accounts for this discrepancy. So it's that little bit you need to add to your model to get the true value, which we don't know. And so the error term is just the difference between yi and yi hat. So there is a difference between the true value and the predicted value. It's basically something we add because we know we can never make a perfect model. Next, we have the RSE. So your residual standard error is one quantity you can use to assess your model. It's basically the standard deviation of an error term, epsilon. The way we can think of it is it basically represents the average amount that a response will deviate from the true regression line. And so this is the formula for calculating RSE. It's considered a measure of the lack of fit of a model. So that means that the lower the RSE, the better a model is, the better the fit. The RSE is nice for assessing a model, but it's not as good as the R square statistics. The reason being your RSE is generally a number, like it could be 2.5 or 3. It's difficult to put it in reference. but your R-square statistic is a proportion, like it's a percentage, so it's easier to understand. And basically, your R-square is a measure of the proportion of variance explained in your response by your model. And so to calculate the R-square, we use the residual sum of squares and the total sum of squares. The total sum of squares being just summing over the difference of each point and subtracting the mean from that and squaring that and taking the sum over that. So the R-square can also be calculated simply by squaring your correlation. Now let's talk a bit about multiple linear regression. So when you have more than one predictor, but you still have one response, that's when you use multiple linear regression. So it's simple. It's similar to simple linear regression. The difference being you have more beta terms and x terms. So and here the parameters beta j are called the regression coefficients. Again, the interpretation is the same. Beta naught is still the intercept, which is the value of our response y when everything else is 0. But the way we think about a given beta j is it represents the change in our response y per unit change in xj, and the caveat being all else held constant. And so the model you see up there will basically generate a hyperplane in k-dimensional space. So one question we should ask is that model y equals beta naught plus beta 1 x plus beta 2 x squared, which looks like a quadratic polynomial, is that a linear model? The answer is yes, because you can simply call x1 equal to x and x2 equal to x squared, and you can rewrite the equation like that, which is a linear a linear regression model. So it's important to keep in mind, unless your beta parameters, unless they themselves are not linear, you have a linear model unless, as long, irrespective of what your x terms are, because you can always do a power transformation like x3 equals x squared. It is also worth noting that the shape of this equation would not be it would not have a linear shape. So it's not required for you to have a linear shape to have a linear model. Okay, so let's talk about some of the potential problems. These are things you want to keep in mind before. It's easy to implement a model in R, but these are some things you want to keep in hindsight to think about what your model means. Is it useful? So first we have non-linearity in the response predicted relationships. So that means, well, if you're using linear models, you expect that there should be a linear relationship between your response and predictor. If you don't, you might have to do things like power transformations. So for example, if you plot your response and predictor and you see that you have, say, a quadratic shape, you know that you need to do a power transformation, and like we did, let x2 equals x squares until you get a linear shape before you do linear modeling. That's something that can be easily checked by a simple scatter plot. Next, we have correlation of error terms. So the way we can check this is by looking at a plot of the residuals. And ideally, we'd like to see it should be random and there should be no pattern. You don't want a correlation between your residuals. Next, non-constant variance of error terms. So for a linear model, we should have constant variance of error terms. So non-constant variance is a problem. So again, the way you check it, you can check it again with the residual plot. And generally you want the height of your plot to be more or less the same. If you see a pattern that's, say, fanning out, then you know your variance is increasing. Next, we have outliers. Again, it depends on the type of outlier you have, but sometimes outliers can influence your model. If they influence your intercept, that's not much of a problem because that just raises your line on the y-axis. But you don't want them to influence your slope. That could be a problem. Speaking of outliers, that brings us to high leverage points. So it depends on, for example, it's important where the outlier is located. If an outlier is located really far away from the cloud of your points, we call it influential because it could change the slope. But if it is suppose located in the center and it's located, even if it's located far away above, it just affects the intercept. Lastly, we have collinearity. So this means that we want to make sure that all the variables are ideally orthogonal in our data frame. And so basically, we don't want multiple variables capturing redundant information. So now let's practically take a look at how to implement this in R. So I've prepared an R Markdown document, which we will step through and do some linear modeling. So for this practicum, we'll be using three packages: Scikit, ggplot2, and statsr. We'll talk more about them. So first, we initialize and load all our packages. This piece of code right here is just a way to make sure that your package you're trying to library in is already installed, so you don't get an error. If it's not installed, it automatically will install it and then library it in. So let's pick a data set. We will work with the mtcars data set. So this is one of the popular built-in data sets that comes with R. And if we take a look, we can simply call it by running data mtcars. And then we use attach. First, let's open up the data frame and look at it. So this is what the data frame looks like. It's a bit small. We can look up the documentation just with a question mark. And here we have descriptions of all the variables. Yeah, and the units. So then we do attach mtcars so that we can call variables without having to call the data frame itself. So what I mean is that typically if I want to access, say, some exploratory data analysis, so I think pairwise correlation plots are great for this because you can look at the relationships of all the variables with each other and just a lot of information in a single plot. So if we run this, and we're going to have to zoom. Okay, this is what it looks like. So you can see this scatter plot of all the variables against each other. And above the diagonal, you have all the correlations. So this gives you a really good idea where to get started. What would you like to model? So if you notice, for say, MPG and weight, the way you'd look at it is you go to the plot right here. So you can see it's reasonably linear, and you can look at the correlation right here. Oh, whoops, sorry, here. And we see a correlation of negative 0.87. That's quite linear. That's a good relationship to model. So we can go ahead and model. Let's pick MPG as our response and weight WT, that is the weight in 1,000 pounds, as our predictor. So again, we just went over the theory, but just to relate it, this is the equation for a simple linear model: y equals beta naught plus beta 1 x plus epsilon. So in this case, remember, we're choosing MPG as y and the weight WT as x. And so beta 1, that is our slope in this context, it represents the expected change in the miles per gallon per unit change in the weight. So, and here a per unit means 1,000 pounds, as we see from the documentation. The intercept gives us the miles per gallon when the weight is 0, but obviously that does not make sense in context because you cannot have a weightless car. So it's really important to put your parameters into context. So the way we build a linear model is really simple. We use the LM function. The call is really simple. Here, basically what I'm doing is I'm building a model where the tilde sign can be interpreted as explained by. So this is just saying build a model where MPG is explained by weight. And we store it in LMFit and then display a summary. So if we run this, it gives us information about our model. Here are the values for intercept and weight. Let's take a look at the values. So the first thing you can notice is if you look at the R squared, which we talked about earlier, we can see that this means that we're able to explain about 75% of the variance in our response, that is MPG, which is not too bad. Then if you take a look at the p-values, that is right here, you can notice that the p-values are nearly 0. That is a good thing. Small p-values usually mean that a relationship is statistically significant. And so if you usually see more than one star at a 0.05 significance level, it's a rule of thumb that you could say that your relationships are significant. When you have large p-values, that means your results are not significant and they could simply be a coincidence. Okay, then just a few simple calls. You have the names function that tells us what is stored in our model lm.fit, and if we run this, we see you have the coefficients, the residuals, fx, and a lot more stuff, and we can access all this stuff simply using the dollar operator as you do. So suppose we want the residuals, so we call them like this. And we can do it for all the other parameters too. We can also use specific functions. So I could either say lm.fit coefficients to see the coefficients, or I could use the coefficient function on lm.fit, get the coefficients, which is what we would get if we ran this. So here, the slope theta 1 is negative 5.3. So that means that we expect that the miles per gallon decreases by 5.3 for an increase in 1,000 pounds of weight. And it's negative. The correlation is negative. That makes sense. The heavier the car, the lower the mileage you expect. The intercept, as we talked about, doesn't make sense in context. Next, we can build confidence intervals. So all you need to do is pass it to the conf_int function, and this will construct a 95% confidence interval. And so you have your lower bound and upper bound for both your intercept and slope. So what this means is that if you take a large number of samples, in 95% of them, the intercept and say the intercept is going to lie between these two numbers. Then let's talk about prediction. Generally, a lot of the times we build models so that we can make predictions. So now that we have a simple linear regression model, we can try and predict our response, that is miles per gallon. And so we can use the predict function. The way we use it is we pass the model, and it's important that we need to pass our response as a data frame with a column name that is identical to the variable name. And so notice that I've named the column WT, which is exactly the same as the variable. And then I've also created a data frame. So if we run this, this will predict what the miles per gallon is for a weight of 2,000 pounds, 3,000 pounds, and 4,000 pounds. These are the predictions. To put it in context, we can make a quick scatter plot. So we plot the weight against PG. You can see the plot here. So for a weight of 2, we predicted 26.6, which is about somewhere here. If you look at the values, they make sense. They're sensible. Then we can work a bit more with the predict function. So we can construct a confidence interval for our prediction. So if we run this, the default is a 95% confidence interval. Notice that the values are the same for fit. Our predicted value is not going to change, but what we're going to get lower and upper bounds. So again, if we take a large number of samples, 95% of the samples, the predicted value is going to lie between the lower bound and the upper bound. That's how we interpret a confidence interval. Next, we can also generate a prediction interval. This is really easy. You do the same thing. The only difference is you specify interval equals prediction. And so now the difference between the confidence interval and prediction interval is that the confidence interval is dealing with your expected value, so y hat, but your prediction interval is dealing with the true value y, and so your prediction interval will always be wider because there's greater uncertainty associated due to the error term, because we are trying to predict the true value and not just the expected value. So if you notice, all the prediction intervals are much wider than the confidence intervals. That makes sense. So now that we've built a linear model, if we want to visualize it, we can use AbLine to plot the regression line on a scatter plot. So if our scatter plot was P and PG, we can draw a line through here simply by running AbLine lm.fit after that. There we go. So this is what our model looks like. That's pretty reasonable. A little bit of sidetrack here. If you use ggplot and you just want to draw a regression line on your data, you don't need to go through the steps of building a linear model and using AbLine. You can use ggplot stat smooth and just say method equals lm, draw a line through your data. So for example, so you specify your aesthetics, your x and y, and then you make a geom point gives you a scatter plot. Then you add another layer, which is just your regression line here. Notice that I'm not passing in lm.fit as the argument. And this is what we get. The grayish area is our confidence interval, a 95% confidence interval. If we don't want that, we can just say SE equals false and just get the regression line. Okay, so in the presentation earlier, we talked about residuals and sum of squares. So let's visualize this with the Shiny app. We can use the plot SS function, which is from the stats R package. So we simply take this and run this in our console. We'll open up a Shiny app right here. So what we can do is we can specify any 2 points and draw, and it'll automatically draw a line. So say my line should go through here. It draws a line, and let's zoom in. Okay, so you see the blue dashed lines, they're your residuals. So it's basically the vertical distance of a point from the line. It tells you by how much your true value is off from your estimated value. That is your error term, the difference between y and y hat. And if you simply square these lines, you get these yellow squares. And so your least squares method is basically trying to minimize the sum of all of these squares. It's a good way to visualize it. And so, okay, when I took 2 points, I got a sum of squares of 523.5. And you can try yourself and see how close you can get to minimizing it, just by visual inspection. So if I try a few times, let's see if we can get any better. Okay, that's not any better. Maybe if I move this here. Nope, only getting worse. So I was able to get, I think my first one was the best, a sum of squares of 523.51. Okay, so now to put this in context, let's take a look at what the NM function generated. So when we actually built the linear model, and see how the algorithm minimizes it. So you can use the ANOVA function for seeing that. ANOVA actually gives a lot of useful information, but we're just going to look at the sum of squares. So looks like the residual sum of squares is 278, which is quite a lot smaller than I could get manually by picking points. But it's good to visualize what you're doing. Okay. So now that we have built our model, let's talk about its diagnostics. So if you recall in the presentation towards the end, we talked about some of the associated problems. So we're going to look at three of them here. So the first one is linearity. And as I said earlier, this can be easily checked by making a simple scatter plot. So if we plot this, you can see that it's reasonable to say that this is linear. If you see a higher order relationship like some sort of like a spline, like a quadratic line or something, that's when you know that you cannot use a linear model. Or if you wanted to do linear modeling, you would simply do a power transformation. So I'd say that this is linear enough to go ahead and do linear modeling. Um, Another way to check is by looking at a plot of the residuals. Um, the next criteria we have is nearly normal residuals. So that means that our residuals should be normally distributed. So you should see like Gaussian curve. So we can take a look at a normal QQ plot for that. And if we run this, this is what it looks like. So ideally, we want all the points to lie on this line. So if you see in the middle, most of the points lie on the line. Towards the end, they go quite off. So sometimes it's difficult to say whether it's okay to go ahead. Is normal condition satisfied? But when in doubt, always ask a statistician. Um, we can also check the normality by making a histogram. So ideally, you'd like to see a Gaussian shape. So Gaussian shape would be something like this, but not the one shown there. It's a bit off. It's slightly, let's see a Gaussian, but not perfect, basically. But that's the way you check. Lastly, let's talk about constant variance. So the way you check this is by plotting the residuals. And remember, we can simply call the residuals by doing lm.fit residuals, uh, or we can simply use the residual function fit. So you plot your predictor against the residuals, and let's make a horizontal line at 0. See what it looks like. Okay. Um, what you don't want to see is a fanning out pattern. So if you see that points that cluster around close to the 0 line and then they start fanning out, that's a bad sign. That's a sign of increasing variance, which is not good. I'd say they look more or less about 0. Um, you also don't want to see any pattern in your data. It's hard to see if there's some sort of pattern here. There are a few points here, but I'd probably say there's no pattern to it, but that's something you want to be aware of. Okay, let's talk about a bit about multiple linear regression. So it's again really similar to simple linear regression. Um, you just add more predictors. So suppose we wanted to again model MPG or miles per gallon, but this time using two predictors. So we use the weight and displacement, so WT and DISP, to predict MPG. So it's really easy. Same call with LM. All you do is you add a plus sign and add another variable. Straightforward. We take a look at the output. You can notice that the intercept close to 0. That's good. The weight is also significant, quite small, the p-value. But if you look at the p-value for the displacement, this is not a good p-value. If you choose a significance level of 0.05, which is typically what you do, you would conclude that displacement is not statistically significant. So essentially a beta 2, which represents the slope, is not statistically significant. Then if you notice here, you have two terms, the multiple R squared and the adjusted R squared. When you do multiple linear regression, what you want to look at is your adjusted R squared. Let's talk about the difference. So your multiple R squared, your regular R squared, whenever you add more variables to your model, it's always going to increase because even if a new variable added is introducing very little new information, it's still improving the model a bit. So your R squared, the variance explained, is always going to increase. But that doesn't necessarily mean you go on adding variables just because you can get incremental improvement. Your adjusted R squared, on the other hand, applies a penalty term for every predictor you go on adding, ensuring that to compensate for the effect of adding more predictors versus the extra variance that is captured. So you'll always notice that your adjusted R squared is lower than your multiple R squared. Um, let's see. So now, if we want to build a model with, say, all the variables in the empty cast data set, so all of these, now you could do lm tilde and type out all the variables using the plus sign. That is cumbersome. Instead, you could simply put a dot, and that signifies all the variables. And so if you run this time you have to specify data equals empty cast. Usually you would specify this, but I haven't been doing that so far because I used attach earlier. So remember that. But with the dot notation, you have to. Okay. If you look at the call, let's see what happens if we add every single variable. So notice for the variables, none of the variables are actually significant. If you look at the p-values, they're all pretty high p-values, not statistically significant. Your multiple R squared, of course, increase. Register R squared increase the bit, but a lot less than your multiple R squared. So now suppose we want to add all the variables in our empty cast model, but suppose we just want to remove this variable here. So it's easy to do that. You just do mpg tilde dot, and then you can use a minus sign to just take out one variable. And it's a similar call. Notice that weight is the only significant parameter here. But yeah, that's how you do that. And then if you go ahead, prediction is pretty similar for multiple linear regression. Again, you can just use the predict function. So say, suppose, what was the second model we built? lm.fit2. So if you recall, this just had two variables, wt and displacement. So if I wanted to make a prediction for MPG, you need to pass two values, what your weight is and what your displacement is. So I do, again, same call predict, lm.fit2, comma. Remember, we need to use the data frame and column names that are the same as your variable. So our variable is wt equals, say, okay, I'll take only one value. Say suppose 2,000 pounds. And your displacement is, what is a good value? So say we pick 150. It's a reasonable value. To get out a value. So again, it's really similar to simple linear regression, just taking it a bit further. And again, you can specify confidence intervals and prediction intervals just by specifying interval equals confidence. So now you might ask, what happens if you have more than one response? That's when you do multivariate regression. That will be covered in tomorrow's tea time. But generally you use multiple linear regression when you have more than one predictor. One of the reasons why linear models are so good is that they're simple, they're easy to interpret. Like if you look at the equation is a simple y equals beta naught plus beta one, you keep adding the terms. So each term has an interpretable meaning. A lot of machine learning methods don't. They're like black boxes. They're great at predicting. But so generally you should start with linear modeling. It's a great start. And then you can look into going beyond linear. Yeah, are there any questions? Yes. The ANOVA function. Okay. If you look up the documentation. Oh, why did I use ANOVA function here? I used it for just looking at the residual sum of squares. So if I do ANOVA, if you look here, I just wanted to look up what the sum of squares was for the residuals. That's the only reason I use ANOVA. You can do a lot more with ANOVA actually, but I just used it just for looking at this residual sum of squares, RSS. Any other questions? Go for it.
That's adjusted R-square
Mhm.
with more
So it's a good question. Not necessarily. So your multiple R squared will increase with more predictors, as because they add at least a little bit more information. But your adjusted R squared does not have to. So if you look at the formula for adjusted R squared, which I did not show actually, but you have a penalty term for the number of predictors. So as you increase the number of predictors, you have a penalty that reduces it. And so it doesn't necessarily have to increase. If it increases, that means that adding the predictor was useful. If it does not, then you know that the penalty was greater than the information introduced by adding a new predictor. Any other questions, comments? Okay, thank you for your attention.